Welcome to EPG Pathashala in Computer Science. We are looking at a series of lectures in computer networks. So, the topic that we will be dealing with today is on multimedia applications. So, if you look at what we have been doing in the past 30 lectures or so, we have been looking at different layers of the network architecture. So, we looked at protocols that are used at the application layer, at the transport layer, and then at the network layer. So, when we talked about the network layer, we also looked at various quality of service parameters and various quality of service related protocols that are supported. Now, the reason we talked about these quality of service parameters is basically for the reason that we need to support multimedia applications. With the demand for multimedia applications and the proliferation of multimedia applications in today's internet, it has become mandatory that the networks are able to support the quality of service that is required to make these applications work properly. So we have looked at different quality of service related support that is available from the network. Now, we are going to move back to the application layer to look at what kind of applications are now used in multimedia and how and what are the characteristics of these applications, so that we can see how well the different quality of service related issues that are there, or the quality of service related solutions that are there are suited for these kind of multimedia applications. It also gives us a method to understand what new techniques have to be developed. So, we will take a look at application layer, we will look at the multimedia applications that are used, and then we will come back to looking at what kind of support is provided specifically for multimedia applications at the transport layer, at the application layer, in terms of handling sessions, in terms of handling the specific characteristics that are required for multimedia applications and so on. So, as a prelude to understanding those things, we are going to look at some of the characteristics of multimedia applications in this particular topic. Okay. So, what we will be looking at is there are different categories with which you can understand multimedia applications. Basically, we talk about content, multimedia content, which means audio, video, images and text that are to be delivered across the network. So, there are three different categories that I said we normally talk about. One is streaming stored content, the other is interactive sessions, and the other is streaming live content. So, we will just take a look at some of the solutions that exist today at the application level, that is different applications which actually allow us to do these things. Then we will go into the details of how these are to be supported from the network. Okay. So, we will start with the taxonomy of real-time applications. We have already looked at this earlier, but we need this again, we need to understand this. So, we will start with this again. So, if you see real-time applications can be divided into tolerant applications and intolerant applications. So, when we talk about tolerant applications, what we essentially mean is that some loss can be tolerated by these applications. So, when you say real time, obviously time becomes a constraint. So, we are more worried about the loss factor. So, here tolerant applications, video and audio type of applications, they can tolerate some losses by using some kind of interpolation techniques. Now, intolerant applications are real time applications which will not be able to tolerate losses. Example of these applications are real applications like your robot control. So, for instance, if you are to control a robot to switch off some machine or something like that, and that particular packet which was sending that command got lost, obviously that is not tolerable, right? You cannot tolerate that. So we have real time applications which are intolerant. Now, when we talk of multimedia applications, they come under this right side category, that is they can tolerate some amount of loss. And even when we talk about tolerant applications, we talk about adaptive applications and non-adaptive applications. When you say adaptive application, it means that you can adjust for change in rate or change in delays, certain characteristics that vary, you will be able to take care of it by adjusting for it. Non-adaptive applications will not allow you for such kind of adaptations. So, when you say adaptive, again we can talk about rate adaptive and delay adaptive. So, when you say rate adaptive applications, what we normally mean by that is that some coding rates or certain coding formats that are used for storing the content or for transferring the content, they can be adjusted to suit the rate that you have. So, if you have a high data rate that is supported, you could have a kind of coding format which takes advantage of that. But if you do not have a very high bandwidth, you can come to a lower a coding which uses less amount of data or less amount of bandwidth. So, you may not get very good quality, but it will still, you will still be able to support those applications. So, that is what we mean by rate adaptive applications. The other category is the delay adaptive applications, where you can adjust for the you can adjust the playback time. So, even if there is a delay, you kind of when you are playing back the audio or video, you can adjust the playback time and therefore give the experience to the user that he is getting a continuous media that is being played. Okay. So, when we look at our multimedia kind of application, they basically come under this category. So, either they are rate adaptive or delay adaptive. So, this is what we will take a look at now. Okay. Right. So, as we said, there are three application types that we will be looking at. One is streaming, stored audio and video. The other is conversational voice or video over IP, and the third one is streaming live audio or video. So, when you talk of streaming stored audio or video, so when you say streaming, it means that that it's being sent continuously, and the playout can begin before we download the entire file. So, which means you do not need the entire file to be downloaded onto your machine before it can be played out. The playout can start even before the entire file is downloaded. So, that is one important aspect. And normally when you talk of stored audio or video that needs to be streamed, it is stored at some server. So, which means that from the server to the client, the data can come fast enough, faster than the rate at which the audio or video will actually have to be rendered. Now, this also gives us an advantage, which is that you can get the data, store it in your client machine briefly, I mean buffer it for some time, and then you can play it from the machine. So, of course, this requires that you need to have some kind of storing or buffering that is required at the client. Okay. Example of these kind of stored streaming are your YouTube, Netflix and so on. Okay. These are commonly used applications that we are very familiar with. Okay. So, when we talk about conversational voice or video over IP, or your video conferences that we have, or voice over IP, Skype kind of applications that we have. So, here we have an interactive application. Typically, it is between two humans who are conversing, right, or on two ends of the network. So, because you have a human to human conversation, you can say that there is some limit on the delay tolerance that you can have. So, for instance, if you compare this with a stored video audio streaming, when I am looking at stored audio video to be streamed, the user may be willing to wait for about 10-15 seconds before the audio or video gets played out. But that is not the case when you are having a conversation with someone, right. So, your conversational voice video or voice or video will normally have more stringent constraints when compared to stored audio video streaming. Okay. And when it comes to streaming live audio and video, the constraints are even more. For instance, when you are, so let us say for instance you have a live sporting event that needs to be streamed. Okay, we talk about cricket, live cricket streaming and so on. So, in these cases the tolerances are even less. So, we need to look at how these things can be handled. Okay. So, if you look at streaming stored video, so we will start with this. Let us look at what are the various techniques that are used and what are the challenges that we have. Okay. So, typically what happens in streaming stored video is that video is recorded at a particular rate. So, for instance 30 frames per second. So, data corresponding to that is stored in a server, and when the video is sent to the client, right. So, the video which is sent is played out at a particular rate, it's sent at a particular rate, and it is received and played out at the client at the same rate of 30 frames per second. But you can see that there is a delay between the time at which the video is sent and the video is received. This delay is basically the network delay that you would have. Now, in this example that is shown here, it is shown as if it is a fixed delay, but in practice it really need not be a fixed delay, this will also vary. But when you receive the data here, you can also play it out at the same 30 frames per second, so that the client is able to view the video correctly. Okay. Now, at this point of time, if you take any point of time starting from the time that you have started playing it out, at this point of time if you look at it, the client will be playing out an early part of the video which is already received, while the server is still sending the later part of the video. So, you are still receiving some data here, but you started playing out the earlier part of the video. Okay. So, this is what happens. Okay. So, what are the various challenges that we have when we talk about streaming stored video? So, one is that you have a continuous playout constraint, that is, once you started your playout, once the client playout begins, the playback must match the original timing. That is, we do not want to have any gaps. Once you started the playout, it has to be a continuous play from there at the same rate at which the original data has been sent, original data has been recorded. Okay. But the problem, the major challenge that we have here is that the network delays are variable. In the previous example, we showed it as if it was happening at a constant, that you always had a constant delay, but that is not the actual case, right. So, which means we have to take into account this variation that you will have in the delays. Okay. That is what we normally refer to as jitter, the variation in delay. Therefore, so what is it that we need? We have to make sure that the client side will buffer enough data to match the playout requirements. So that's our one major challenge. Other challenges that we have to deal with are, you'll also have to provide for client interactivity. Typically, when you're viewing a video, you may want to pause, you may want to fast forward, you may want to rewind, you may want to jump through the video, a normal remote control kind of operation that you would like to do. So you need to have some support for these kind of operations as well. So that's another thing that you require. Third thing that could happen is that video packets may be lost or may be retransmitted. Again, depends on what kind of loss management mechanisms we use. So they may be lost, in which case how do you account for that loss? Okay, how are you going to adapt to that loss? So those are some of the things we need to look at. Okay, so let's look at this again. So we talked about the data being generated at a constant rate and sent at a constant rate. But we said the network delay can be variable. So when the network delay is variable, you can see that this is obtained within a certain delay, but you can see that the next packet is delayed for a longer time. Okay, and here you can see that there is even longer a delay that you have. Okay, so what do we do in this case? So you have to make sure that your playout delay, your client playout delay, is displaced by some amount of time. Okay, is put off by some amount of time, so that when you start playing, you will be able to play all the data without any gap, right? Without having to block for reception of data. So that is what we need to keep in mind. Okay. So during this time, you have your buffered video, right? And you have to compensate for the network added delay and the delay jitter. So you cannot assume the delay will always be constant. There will also be a jitter. So you need to make sure that this playout delay that you have takes into account both the delay and the delay jitter factors. Okay. So let's look at how that is normally handled. So we said we need to have a buffer, and it's important for us to determine what should be the size of this buffer. So the buffer size has to be such that you will be having data coming in at a particular rate, right? The filling rate, let's say that is x of t, and that is a variable rate because you will have data coming in at various rates. But the rate at which it gets played out, that will be a constant rate. It's a constant bit rate, let's say r. Okay. Now let's look at what will happen here. Okay. So initially what will happen, your buffer will get filled, okay, until the playout begins at some time tp. Now tp is that was our variable point at which we are beginning the playout. Okay. So the playout is beginning at tp. So you can see that the buffer will fill, okay, the buffer will fill as the data comes in, and the level will vary over time as the fill rate x of t varies. Okay, this will vary, but this is constant. So we saw that, for instance, that there is a variation in the, so you can see this variation, right? It's getting filled up, right? And then you can see that as it is getting played out and as data is received, this variation you have in this size of the buffer that you have. Okay, so this is something that will be there. So you have to make sure that you are able to manage this buffering on the client side appropriately. Okay. So there is obviously a relationship between the rate at which it is getting filled and the rate at which it is being played. So if your x of t is less than r, that is the average fill rate, let's say is x bar, okay, let's say that is less than the playout rate r. Now remember this varies over t, so we take the average rate x. So if you take the average x, and if this average rate x is less than r, then what will happen? Eventually the buffer will empty out because you are sending it out at a rate which is faster than the rate at which it is coming in. So what will happen now? So you would have played out your data and you still have no data to play. So what will happen? It will cause freezing of the video playout until the buffer fills up again. So you will have this freezing of video that happens. Many of you would have experienced it when you are actually viewing some videos, right? So this is something that could happen. The other cases where x is greater than r. So now what will happen, since x is greater than r, the buffer will not be empty. Okay, provided your playout delay is large enough to absorb the variability in x of t. Okay. Of course, you have to make sure that your buffer size is also large enough that you don't lose any data, right? Because your buffer should not get filled up and overflow, that you are not able to hold the data. Okay, that's important. So you can see that there is a slight trade-off that we have between the initial playout and the delay. So buffer starvation is less likely if you have a larger delay, right? If your delay is larger, obviously you will have less of buffer starvation, but the larger delay will delay the users watching of the video, right? Because here they have to wait for a longer time before they can start viewing it. So you need to have a kind of this is a trade-off, so you need to choose the appropriate value over there. Okay, so this is one of the important things to look at. So often what happens is that the server sends at a rate which is appropriate for the client, and the send rate is normally equal to encoding rate, and that is equal to a constant rate. So that is the way it is normally fixed. And the transmission rate can be oblivious to congestion levels. So now this is the case that we have when you are streaming multimedia over UDP. So we have different options at which you can be streaming multimedia. You can be streaming it on top of UDP or TCP, okay, or use other mechanisms. So we look at each of these strategies that are possible. So when we stream data over UDP, so this is what will happen. You will just send it at the rate at which it has been encoded, and it, since UDP does not worry about congestion control or anything, so the transmission rate will not worry about congestion, so it just gets transmitted at a particular same rate. Okay. Now normally what is done is you can use a short playout delay or 2 to 5 seconds to remove the network jitter, and any error recovery that is required will have to be taken care of at the application level. Okay, the application will have to handle any error recovery because UDP will not take care of any error recovery mechanisms. And one challenge we have when we use UDP is that UDP may not go through firewalls. So in that case you may be restricted in terms of your viewing that content which is streamed over UDP. So these are the issues that we have when you are looking at streaming multimedia over UDP. So the next option we have is streaming multimedia using the HTTP protocol itself. That is, you are trying to retrieve the multimedia file using the HTTP get function. Okay, we have a get method in HTTP. So use that to retrieve the content. So and then you can send it the maximum possible rate under TCP. So that is the rate at which you will be able to send it. But remember what will happen here, other than your application playout buffer, there will also be a TCP receive buffer where the data will be sent, and from the TCP receive buffer it will be sent to your application playout buffer, and then you will start sending the data. Okay. So the fill rate will fluctuate due to TCP congestion control, retransmissions and so on. So remember, TCP will take care of all these things because of congestion control and retransmissions. The rate at which your data is coming in will vary. Okay, so that is something that we need to take care of in this case. Okay, and a larger playout delay obviously will smooth the TCP delivery rate, so you will have a better playing experience. Okay. And another advantage of going through HTTP based mechanism is that HTTP runs on top of TCP. So this HTTP TCP combination may pass through firewalls easily. So you may not have too many restrictions that you are not able to view this content because of the underlying protocol. Okay, so this is another option that is used. Okay. So yet another option that we have is streaming multimedia using a protocol called DASH, which is basically dynamic adaptive streaming over HTTP. So it kind of uses HTTP but provides some kind of an adaptive streaming mechanism. So the idea that is used in this methodology is this: the server will divide the video file into multiple chunks. So each chunk is stored and encoded at different rates. So you have the same file stored at different rates, so different encodings are used. And there is something called a manifest file which provides URLs for different chunks. So that is, for different rates you have different URLs from which you can get the file. Okay. So what is it the client will do? The client will periodically measure the server to client bandwidth. So depending on the server to client bandwidth, whether you have a high bandwidth or a low bandwidth or and so on, the client can consult the manifest file, okay, to choose the one which suits its bandwidth, its current bandwidth. So it requests one chunk at a time. Okay. So it will choose the maximum coding rate which is sustainable given its current bandwidth. Okay. So then by choosing different coding rates at different points of time, you can account for the variation that you have in the bandwidth. So if you have a higher bandwidth, in between you could go for a higher coding rate, which means you may get better quality video. But when your bandwidth drops, you can go for a low quality video, and therefore, but still your entire flow will not be broken. So that is the idea that is used in this dynamic adaptive streaming over HTTP. Okay. So when we talk about this DASH, the intelligence basically is at the client, because the client has to determine the bandwidth quality, right. So the client has to determine when to request chunk, so that the buffer starvation will not occur or some overflow does not occur. Either the buffer should not become empty or the buffer should not become totally full that you are losing data, right. So you need to keep track of when to request the chunk and what encoding rate to request. So higher quality when more bandwidth is available, that choice has to be made by the client, and where to request the chunk. Okay, so that is from which URL server can request in the URL server that is close to the client or has the highest available bandwidth. Okay, so you can choose if there are multiple URLs available where the same content is available with the same encoding. You have to choose between one of those which is best suitable for the client. Okay, so these are the decisions that have to be taken at the client. So we say that the client has to be intelligent enough make effective use of the dynamic adaptive streaming over HTTP mechanism. Okay. So that is about streaming stored video. Okay. So the next application that we want to look at, or the next major multimedia application category we want to look at, is the interactive category. Now our voice over IP, that is sending audio streams, interactive audio over the IP protocol. Now that is a very important application that we need to consider under this category. So we will take a look at the features that need to be supported for voice over IP. Okay. So one of the first challenges or constraints that we have, or let us say requirement that we have, is a end-to-end delay requirement. So remember, it's a conversation between two users. So since it is a conversation, you can't have very high delays. Okay. If you have very high delays, they are noticeable and they will impair the interactivity that we have. Okay. For instance, less than 150 milliseconds is good. The user will not be able to perceive that delay. So it will almost feel like you are having a continuous conversation. But if your delay is greater than 400 milliseconds, it will be bad. You will be able to see that there is a delay and it will kind of affect your conversation. Okay. So when you say delay, this delay includes all delays that are possible. That is, from the application level, the packetization delay, the playout delay, plus the other network delays that are there. So all this included ideally should be less than 150 milliseconds, and it should not be greater than 400 milliseconds. So that's the requirement that we have first. Okay. Second thing is, you will also need some support for initialization of sessions, because you need to have a session between the two ends, right? Because the conversation will take place over some amount of time. So how does the callee advertise the IP address, port number, encoding algorithms to be used? Okay, how do you make sure that the session is set up? Okay, there are some support that is required. There is some support that's required for this as well. Okay. In addition to that, you may have, since you're talking about a voice call, there are some value added services that are normally expected of voice calls, right? You may want to have something like call forwarding, screening of calls, recording of calls, okay, some emergency services. So all these also may be additional requirements, functional requirements that will have to be provided. And to suit these functional requirements, we may need to do something from the network side as well. Okay. Another important characteristic of the speaker's audio is that there would be alternating talk spurts. For instance, you talk and there will be some silent periods in between, okay, and then again there will be a talk spurt. Okay. So, and when the talk spurt is there, that is when the conversation is going on, when the voice is being heard, normally you will have a data rate of about 64 kilobits per second. Now remember 64 kilobits per second because we sample voice at a rate of 8 kilohertz, and if you are using even 8 bits per sample, it will come to about 64 kilobits per second as our rate. Okay. So the packets are generated only during the talk spurts, so we don't have to generate packets for the silent periods. And so if you look at the rate at which it actually will be generated, you will see that every 20 milliseconds you will have chunk of 8 kilobytes per second of data that's being generated. So it comes to about 160 bytes of data. Okay, this is for every 20 milliseconds you will have about 160 bytes of data that are going to be generated, right? So that's based on our sampling period and the number of bits that we have per sample. Okay. And an application layer header is added to each chunk. So this chunk plus header will be encapsulated into a UDP or a TCP segment, okay, and this will be sent into the socket. So every 20 milliseconds during the talk spurt. So this is typically what your voice over IP characteristics will be like. Okay. Now when this is being transmitted, there are losses that can occur. Now why would loss occur? One loss could be because of the network delay itself. Remember, it's after all running on top of IP, and IP is a best effort service. So IP datagrams can be lost due to network congestion or due to router buffer overflow and so on. Okay. There's another type of loss that can occur, which is the delay loss. That is, the IP datagram arrives at the receiver a little late, okay, not just a little late, you can say it's too late for the playout at the receiver. That is, you have begun playout, you expect a packet to come in at a particular point of time, but it has not arrived at that point of time. So what do? You can't play that packet obviously. If it comes later than that time, its time is already over, so you cannot play it out. So that also will amount to a loss. So we have to take care of this loss as well. Okay. So as we said, typical maximum tolerable delay is 400 milliseconds. So you may delay your playback time by about 400 milliseconds, but if you delay it by 400 milliseconds, already that is not going to be very comfortable for the user as such. Okay. So we need to look at what kind of loss tolerance features can be built in. So depending on the voice encoding that we use, some kind of loss concealment or packet loss rates between 1% to 10% can be tolerated. Okay. So that's what you normally have here. So if you look at the delay jitter, this is something that we just talked about, right? Just as when we talked about streaming video, we have a delay jitter, same kind of mechanism will occur with respect to audio as well. And this is our play out delay that you have, right? So this is your buffered data. So as we said, end-to-end delays of 2 consecutive packets, this difference can be more or less than 20 milliseconds. That's the transmission time difference. Okay, actual end-to-end delay may be a little more than 20 milliseconds or less than 20 milliseconds. So that is a possibility. Okay, so how do we handle this? So typically what we do is the receiver will attempt to play out each chunk exactly q milliseconds after the chunk was generated. Okay, so this is when we have what is called as a fixed play out delay. So if you, this is one option of delivering a voice over IP. We know that there will be a delay, but and therefore you use a fixed play out delay. Let's say some q milliseconds is our fixed play out delay that we have. Now what will happen in this case? So the chunk will have some timestamp t. So which means you will play out the chunk at a time t plus q. So you have received it before t plus q and you are going to play it out at t plus q. So if the chunk arrives after t plus q, that is the data arrives too late for the play out, you consider the data to be lost. Okay. So there is obviously a trade off in choosing this queue. So if you choose a large queue, obviously less packet loss, but the experience will not be good. If you choose a smaller queue, you have a better interactive experience, but you are likely to lose packets. So you need to choose an appropriate queue here. Okay. So this is 2 examples of choosing 2 different values. So this corresponds to choosing a playback time of delay of p. Okay. If you start at p, you can see that in this case, some packets arrive before the playback time and some are lost. So you can see here, for instance, this packet should have arrived at this point of time, but it arrives only over here. Therefore, this packet will be lost, right? You can see how this play out is actually taking place. Instead, if your playback had started as a p dash and this was your play out schedule, so you will find that here the packet would have arrived before the playback had to start. Therefore, you will be able to play back the data correctly. Okay. So how do I choose? Do I choose p or p dash? What is it that you do? Okay, that is where the key thing comes in. Okay. So what we do for this is, instead of having a fixed play out delay, we try to have an adaptive play out delay. So what do we mean by an adaptive play out delay? So the goal for adaptive play out delay is that you want to have a low play out delay and have a low late loss rate. That is, because of packets arriving late, losses should not occur. So that rate we want to reduce. Okay. So the basic approach to use is that you want to have an adaptive play out delay adjustment, which means you will estimate the network delay and adjust the play out delay at the beginning of each talk spurt. Don't use a constant play out delay for all talk spurts, but at the beginning of each talk spurt, look at what the delay has been, okay, so far, and based on that you adjust the play out delay. The silent periods can be compressed and elongated. Okay, so that's a possibility that we have. So chunks will still be played out at the same that every 20 millisecond it has to be played out. Okay, during talk spurt, that is what will have to be done. Okay. So how do we do that? We need to do some kind of an estimation of the packet delay. So what do we do for that? We again go back to our standard mechanism of using some exponential weighted moving average. Remember, this is how we calculated the round trip time in TCP. Okay. So we go back to the same kind of mechanism and calculate the estimate packet, average packet delay, or what we call as the exponential weighted moving average. So why do we say exponentially weighted moving average? So you can see what we are doing here. So you take you have your Ri minus Ti. Ri is the time at which the packet is received. Ti is the time at which it was sent. That is your timestamp. So Ri minus Ti gives you the measured delay for the ith packet. So this measured delay for a particular packet is weighted by a factor of alpha, and previous values that you had, your previous delay that you had, that is set to Di minus 1. That is multiplied by a factor of 1 minus alpha, so small constant, for instance 0.1 or whatever, and your Di is calculated as the weighted average of these two factors. That is the current value plus your previous value. So for your Di plus 1, now this Di will be multiplied by 1 minus alpha, and you will be using the new values of Ra plus 1 and Ti plus 1 to calculate this delay. Okay, so this is how the average delay is calculated. Now similar averaging can be done to also calculate the deviation of delay, right? How much the deviation, there is the average jitter that you have. So how do I calculate the jitter? Remember, this is what we do, right? Ra minus Ti gives me the current difference. You subtract the previous difference, Di, the original value that you had from that. So that gives you your the variation in the delay. So this variation in delay is multiplied by a factor of beta and added with 1 minus beta times Vi minus 1, the previous variation that you had. So again, weighted average of the current deviation value with the previous deviation value. So once you have your Di and Vi calculated for every received packet, Okay, so what we do is you calculate the playout time for the first packet. So how do I calculate the playout time for the first packet? You take it as Ti plus the time at which it was transmitted plus Di, the delay, the average delay that you have, plus K times Vi. Now K is a constant factor which may be a value of approximately 4 or something like that is normally used. So you are accounting for some variation in the delay multiplied by some value plus the delay. So this is some amount of adjustable, or you can say it's adaptive to the current situation. You're measuring the current delay, current variation, and based on that you're setting what the playout time is. Okay, this is something that is done. Okay. So the question that we need to answer here are, how will the receiver determine whether the packet is the first in the talk spurt? That's what, because we are saying that we'll start doing it from the first packet in the talk spurt. So what we do for this is, if there is no loss, obviously you can look at successive timestamps. So if the difference of successive timestamps is greater than 20 milliseconds, it means that a talk spurt has begun. Okay, so that is one way to look at it. But if a loss is possible, right, which means this difference of greater than 20 milliseconds could have been because a packet was lost. So in which case, you don't not only look for the timestamp, but you should also have some sequence numbers given to the packet. So you can then look at the sequence numbers and see if there is a difference of successive timestamps greater than 20 milliseconds and the sequence number is without gaps, then a talk spurt can begin. Okay, so that's how you can keep track of when a talk spurt is going to begin and start your calculations based on that. Okay. So now how do I recover from packet loss? That's another issue that we had, right? One way to take care of packet loss will be do a retransmission, but obviously not a very good solution because each ACK will take up about 1 RTT, so delays will be higher. So the another alternative to this is that you can have some kind of a forward error correction mechanism. So you can send enough bits to allow recovery without having to retransmit. That is, we are using some kind of redundant encoding techniques, okay, redundancy based techniques. So what we mean by forward error correction is that a simple example of forward error correction mechanism could be something like this. So for every group of n chunks, you create a redundant chunk. Okay, so let's say by exclusive ORing the n original chunks. So now when you have to send actually n chunks, you actually send n plus 1 chunks. So this actually will increase the bandwidth by a factor of 1 by n because you are sending more data. Okay, but what happens is that you can reconstruct the original n chunks if at most one chunk has been lost in this n plus 1 chunks without any playout delay. I mean with of course some playout delay. Okay, that is, because you are doing an XOR, if only one particular packet was lost, you can always XOR with this n plus 1th packet, which is an XOR of these, and you will get back your original data. Right? So this is one simple XOR based FEC mechanism that could be used. There are other FEC mechanisms that are used, which is that you can have your original stream of data, right? That original stream of data can be now encoded using two different resolutions, two different packet encoding schemes. So I will have a high resolution stream and also a low resolution stream, and this low resolution stream you can see is sent with the next packet that is being sent. That is, I send one packet at a high rate, and then when I am sending the next packet, I send along with that a low resolution packet of the first packet. So the same thing will happen. So you can see now, if a packet 3 is lost, which had the full, which will have data of 2 and low resolution of 2 plus the original 3. If this was lost, now what happens? After all, you will get a low resolution 3 in the next packet. So I can use this now to replay my third data. Okay. So if you have a non-consecutive loss, the receiver can conceal the loss. So in general, you can say not only have just the one low bit rate data, you can also have n minus first and n minus second low bit data chunks that can be sent. So you can have multiple low bit data chunks that are sent, and you can use that to recover the data. So this is one option that you could use. Okay. So for instance, if you are sending nominal stream at 64 kilobit per second, a redundant stream can be sent at 13 kilobit per second. So you could still get your data from the other packets. Okay, that's one option. The third option that we have is using some kind of an interleaving to conceal the loss. That is, you have your original stream which consists of 1, 2, 3, 4, 5, 6, 7, 8 and so on. So what we do is you group it into some groups, okay, some smaller units. So if I have 16 packets to be sent, group it into units of 4 and pick one packet from each of these units. So I will take 1, 5, 9 and 13, make this as my one packet that I am sending. Okay. So if you see what happens here, you can see that there are different packets that are there, not consecutive packets, which are there in the in a single packet. So if one particular packet is lost, what is it that I have lost? Let's say this packet gets lost. 3, 7, 11 and 15 are lost. So at the received end, one is obtained, 2 is obtained, only 4 is obtained, 3 has been lost. Similarly here 5, 6 are obtained, 7 is lost. So what can I do now? I can have some kind of a reconstruction mechanism where I may use some interpolation or averaging based on the data that I have, and based on that I can try to reconstruct this packet, or it may even be such that even though I have lost only one packet of data, you may not perceive that loss. Okay, so that is another possibility that we have. So no redundancy overhead, but of course will increase your play out delay a little bit. Okay, so that is the idea that is used over here. Okay, so an example of voice over IP is Skype. We will just quickly run through how Skype basically works. Skype uses encrypted messages. It is a proprietary protocol that it uses. So you have different components of Skype. We have clients, Skype clients, basically the ones who are making the call, and then there is something called super nodes. Okay, a Skype super node. These are Skype nodes with some special functions. And then we have an overlay network, which is basically a network of these SNs, which is used to locate where the Skype clients are present, and there is a login server. Okay, so if you look at what happens in this case, the typical Skype client operation, let us say user joins the Skype network by contacting the SN, the IP address is attached, okay, using TCP. So you will log in the user by giving your username, password, etc. to the centralized server using the login server. Now you have to get the IP address of the callee. Okay, where do you get the IP address from? You could get it either from the SN, that is a super node that you have, or using the super node overlay, okay, or by using some kind of client buddy list or whatever that you may have. Okay, you get the IP address, and once you obtain the IP address, you can directly talk to the to that particular callee, okay, that you are trying to talk to. Okay, this is the basic idea that is used. Now, one of the nice things about Skype is that suppose the two the caller and the callee, okay, the two users are both behind NATs, and you know, that is they are not able to access. You have some kind of network address translation mechanism that is available. So what will happen is that from an outside peer will not be able to initiate a conversation with the inside peer, but the inside peer can initiate a connection to the outside. So with the help of Skype and the supernode concept, this kind of a mechanism can be very easily handled. So let us look at how that is done. Okay. So basically what happens is both Alice and Bob can maintain a connection with their supernodes. Okay. So this has a connection here, this has a connection here. So what will happen is that Alice will signal her SN now to connect to Bob. So Alice SN will connect to Bob's SN, okay, and now Bob's SN will connect to Bob using the already established connection that they have, okay, because Bob can call this SN, so they already have an established connection there, so using that they can talk to each other. So this is one very interesting aspect of how with the help of the super nodes we are taking care of these things. So to summarize, what we have tried to highlight in this talk is that we try to look at the features that are there of two different multimedia applications. We looked at one is stored video streaming, how that is handled, and then we looked at the voice over IP, which is basically an interactive audio streaming mechanism. So we looked at the approaches that are possible and that ones that are currently used. Okay. So what we have also done by means of this is that we have tried to point to need for protocols to support multimedia applications. Right? We saw that you need to have timestamps, you need to have sequence numbers and so on. So how are these things to be supported? How is it that we can have protocols in order to support these kind of applications? So that is our topic for the next few lectures. Okay? So we will take a look at those things. So this should give you an idea of the characteristics of multimedia applications. Thank you.